Okay, welcome everyone. It's 1 o'clock, so let's start as we mean to go on and start on time. So lovely to see so many people here joining us for this inaugural online ESICUP meeting. I'll just take just a minute or two to welcome everyone and say a few thank yous and a few housekeeping notes. So first of all, I'd like to say thank you to Fran, who has volunteered 2 years in a row to hold the ESICUP meeting in Toledo. Last year being completely thwarted by COVID, and this year us having to go online. But next year, we are absolutely hoping that we will all be together in person in Toledo. So do make a note in your diary, and fingers crossed we will be able to travel and all sit in the same room together, albeit wearing face masks or whatever we need to do. Also, just to say thank you to Tony Martinez, who has done so much work answering emails and pulling the programme together and keeping it on top of everything to make sure that we are all here at this moment in time ready to take part in the conference. And finally, just thank you to all the others on the ESICUP committee who have answered my emails as I have wrung my hands wondering what to do about the next meeting and offered support. So we've got a great programme ahead. We've got 30 talks. I think we've still got 30 talks. It might have gone down to 29 recently, plus 4 tutorials. I think one of the benefits of being online is that we are able to invite people who might not have been able to spend the time physically traveling to be with us. We've able to invite them to give a tutorial in the session. So particularly looking forward to those. Just a couple of housekeeping notes. I'm sure you're all very accustomed to using Zoom, Teams, or whatever other different platforms that are around. So please keep your microphone on mute so we don't get any background noise. Up to you whether you keep your video on or not, but if you're struggling with internet bandwidth, then it might be good to keep your video off. We'll have questions at the end of each talk in the normal way. There's 2 ways you can ask questions. You can either use the raise your hand button in Zoom, which is under reactions. And I think it might also be under the participant bar. Zoom keeps changing how it works. No, maybe not. But on the bottom of your screen, you should see reactions, and there's a button where you can raise your hand, and we'll see that you've raised your hand and invite you then to unmute and ask your question at the end. Alternatively, you can use the chat function to ask your question, and the chair of the session will try and pull your question out of there. But ideally, use the raise the hand button to ask questions at the end. So we'll start our programme in just a moment. I hope you're all able to engage as much as possible over the next 4 days. We've tried to keep the sessions to 1 hour with a 15-minute break in order so we don't get fatigued being on the screen all the time. But please do try and join in as much as possible. I know it's always tempting to slip in the odd other meeting here and there, which we understand sometimes needs to happen. When we do take a break, we have 15-minute breaks. Please, if possible, stay signed in to Zoom. You don't need to leave Zoom, just turn off your microphone, turn off your camera, and then you can rejoin without having to go through the entry process again. Okay, so I'm delighted to be able to share with you our programme and our first speaker, and I'm now suddenly thinking I need to remember the title, and so therefore need to find the programme online. Excuse me, this is not very slick.
I can help you, Julia, if you want.
I'm there. So welcome Manuel Iori as our first guest tutorial speaker, who'll be talking about combinatorial benders decomposition for 2-dimensional packing problems. So over to you, Manuel.
Thank you very much, Julia. So I had a moment in which everything froze, so I hope my connection will remain okay. And please, in case you don't hear me, just write or tell something to me. So I try now to share my video. Can you confirm you can see the slides? Okay.
Yes, we can.
Okay, so thank you very much, Giulia, Tony, all the team. I know you worked so hard to organize the conference. So you did it last year, you're doing this year, and from what I got from your talk, your introduction, Giulia, you're doing it also in 2021. So a lot of work. Thank you really for all of this effort. So I'm pleased to start this first session by discussing exact methods, and in particular, combinatorial Benders decomposition method for two-dimensional packing problems. So I will, let's see, I will briefly introduce the cutting and packing area, but I'm sure you are all aware of it. Then I'll try to focus on the basic decomposition scheme that we apply. And then I'll try to discuss these decomposition schemes in several applications, including strip packing with rotation, and beam packing. And the idea is to provide some improvements to the basic scheme that can be useful not only for the problems we addressed, but for a large variety of problems in a 2D packing. And then we will conclude with some future research direction and remarks. So, first of all, the two-dimensional packing. So we are given a set of items. They are rectangles, and they are numbered from 1 to n. They have a width, wj, and a height, hj. And we have one or more bins with width w0 and height h0. And we want to pack the items without overlapping into the bins by minimizing a certain objective function. You are well aware that these problems are very challenging. They are studied since the 60s. And they can model many real-world situations, like optimizing areas, cutting materials with minimum waste, loading cargos, scheduling under spatial constraints, stacking on piles, defining a layout, and so on and so forth. Here we will focus on 4 main problems. The two-dimensional orthogonal packing problem is the very basic problem in which we are given a set of items in a single bin, and you want to check if these items fit without overlapping into the bin. Then we can see some extensions of this basic problem. Like in the knapsack problem, the items have a profit, and we want to pack the subset of items of largest profit. In the strip packing, we still have one bin, but this bin has infinite height, and we want to pack all items in such a way that the bin is called the strip, in this case, height is minimized. And in the two-dimensional bin packing, again, we want to pack all the items, but we have multiple bins, they are identical, and we want to pack them into the minimum number of bins. So all these problems are NP-hard. They're actually strongly NP-hard and very difficult in practice. Even the simpler orthogonal packing problem might require, if one wanted to solve it with a basic enumeration scheme, it might require order of n to the power of n nodes. In addition to that, there are many variants, which we are not going to discuss in this talk, but that can be used to better represent real-world requirements, like rotation of items, guillotine cuts, precedences, or incompatibilities. I'd like to mention the recent result, the recent survey that appeared on EJOR with Vinicius Lotti de Lima, Silvano Martello, Flavio Miyazawa, and Michele Monaci, in which we surveyed more than 150 papers, mostly focusing on exact methods in the last 2 decades. So there is still a lot of research going on in this area, also in terms of exact methods. And the research is well motivated because there are instances with 20 items that remain unsolved to proven optimality despite decades of research. So there is need of good mathematical models and good solution algorithms. So let's see the first of such a mathematical model and how we can decompose it. So a good relaxation is the one in which we forget about the problem here in the left. I hope you can see my mouse. And we focus on the problem on the right. What is the problem on the right? It's a problem that we obtained from the original 2D packing problem by cutting items and bins into unit width vertical slices. And then we ensure that we ensure to pack these slices in such a way that all slices of an item are contiguous one to another. So you can see here the orange item, and you can see it has been cut into several slices, and they are packed contiguous one to another. You can think of these columns as one-dimensional bins or as processors. And according to the way you see this relaxation, you can have different problems, which are very similar one to the other. The parallel processor scheduling problem with contiguity, or the bin packing problem with contiguity, or probably the first one, the bar relaxation by Scheitauer, that was back in 1999. And that is a good relaxation. It is strongly NP-hard to solve this problem, but not as difficult in practice as the original problem. And we can get a very good bound, so very good estimation of the objective function value. So let us introduce just one slide with some notation. Capital W, 0, 1 up to W0 minus 1 is the set of columns along the bin width. So all the columns we obtain after the cutting. Capital H is the set of rows along the bin height. And then WJQ is the subset of columns such that if I pack item J with my left border on one of these columns, then item J will occupy column Q. Let us consider the example. This is column Q. Item J as with Wj. If I pack it in Q minus Wj plus 1, then I will occupy column Q. My height will be here. And again, if I pack it in Q minus Wj plus 2, I will occupy it again until I pack it in Q. So the set is all the integer numbers from Q minus Wj plus 1 up to Q. And the same happens along the rows. So on the HJT is the subset of rows where item J would occupy row T. We could decrease this with normal patterns. We forget for the moment about that, and we will study these patterns later on in the applications. So using this notation, we can provide the first model for the orthogonal packing problem, the basic feasibility check. We need two variables. The first variable xjp takes value 1 if item j is packed with its left border in P and 0 otherwise. nyjr takes value 1 similarly if item j is packed with its bottom border in R, 0 otherwise. So we have x and y coordinates. And then we forget for a moment about 1. Constraint 2, each item is assigned to an x. Constraint 3, each item is assigned to y position. And then constraint 4, the nasty one. If we consider a certain position, a certain unit width, unit height square at column Q, row T, then there cannot be two different items that both occupy that square. And that implies that the sum over these 4 summations should be at most 3. This is a non-overlapping constraint, and expressed in this way, it is very bad. It's very bad because you can assume, you can see, it will destroy the linear relaxation of the model. It will make it very highly fractional. Then we have binary variables, and then constraint 1, which simply reports that the sum of the height in each column is at most the height of the bin. This is redundant for this model. And this model is not very effective in practice, not at all. So what we can do, we can try to obtain a better model through a decomposition scheme. So first of all, we project out from the model the y variables and the relative constraints. And we obtain the good relaxation, which can be called the parallel processor scheduling problem with contiguity, or bar relaxation for short. Here what we have, the sum of the height in each column is at most the height of the bin. This constraint, before it was dummy, but now it's important. And each item is packed. And then the x variable is binary. And we can suppose we have an algorithm, a tool to solve this model. And once we have solved this model, we are left with a solution S. Now we have feasible X variables. Now we want to check if we can build feasible Y variables. So let's consider XJPS as the solution of the previous model. And let us define PJS as the coordinate of the left border of J in solution S. And that's simply obtained by this summation, because among all these X variables, I will take just one of them. So the problem of finding feasible Y variables becomes what we call Y check. So now we have the Y variables of before. We want each of them to be packed in a bin, and we want non-overlapping. And now the non-overlapping has become stronger. There is still, again, our 1 unit width, 1 unit weight, height square, but we already know if an item is overlapping on the X column. So we can devise a unique summation for all the pairwise constraints and obtain a clique inequality. And this is a stronger model with respect to what we have before. And of course, variables are binary. So we can send this model to CPLEX, or we can devise a solution algorithm for this. And then we will have two possible outputs. If the Y variables are feasibly determined, then we have a feasible solution for the original 2D problem, and so we are done. Otherwise, we have to forbid the original solution on the X variables. And so we added this that we can call, I don't know if you can see the bottom of my slide, I cannot, but that we call no good cut, or Bender's feasibility cut. Among all the X variables that you selected, at most the cardinality of n-1 can be selected again at the next iteration. And so what we have is a better model for the orthogonal packing. Respect the maximum height of the bin on each column, assign each item, remove solutions which are infeasible for the Y variables, and binary variables. This is a better model because it has a good relaxation, but of course, solving the problem even without this line is difficult, and there are many, exponentially many possible constraints here of type 3. So we need to define a way to tackle this difficulty. The fact is that in addition to these two previous difficulties, we have another one. Solving Y check is NP complete. So you can see it here. I will do it very quickly. If you do proofs of complexity in packing, usually you end up with partition. In partition, you have a set of weighted items, and you want to divide it into two subsets in such a way that these two subsets have the same weight. And you can see the structure here. There is only a single solution, apart from symmetries, for these white items. So we are left with two empty spaces. They have both sides B. So suppose we have many items, we can fill the items here only if we can solve partition. But since partition is NP complete, then also Y check is NP complete. And in fact, we could prove that this is strongly NP complete, so very difficult. In fact, we can solve most of the instances, but some of them are really difficult in practice. So you can see here, for example, the optimal solution for instance CGCAT03. On the left, you see the bar relaxation solution. And on the right, you can see the reconstruction after Y check has been solved. You can see it's not trivial to obtain that solution. There is just one item that has some free space, and here a lot of non-guillotinable patterns, which, by the way, are very difficult to find with heuristics. It's not easy to produce stuff like that. So let's see, now that we have this basic scheme, now we know it has some problems, some difficulties to be solved. Now let's see how we can improve the basic scheme and how can we apply it to some problems. We will have three such problems. The first one is the strip packing problem. So we have one bin, infinite height, and we want to minimize the height. What we discussed so far was a joint work with Jean-François Coté and Dell'Amico, and it was published in 2014. So we proposed the decomposition discussed, and we embedded it into a linear search between a lower and an upper bound on the strip height. Usually these two values are very tight. You fix a threshold height, and then you solve the orthogonal packing decomposition. We solved the white check with an ad hoc combinatorial branch and bound, and we propose some improvements. I'd like to discuss two improvements, as I believe they can be reused for many other problems. The first improvement is called Combinatorial Benders cut, and it builds upon the fact that finding this constraint requires solving white check, but then what we get is something very weak. Suppose you have 100 items. This constraint will only tell you that among the previous solution, you can select 99 of those variables, just one is forbidden. So it has a very limited impact on the next linear relaxation solution. We can improve this by looking for a minimal infeasible subset. So looking for the smallest subset C of items such that the cut remains violated. So instead of 100 items, we are looking for this subset, maybe 20, 30 items that are still causing infeasibilities. You might expect that some very small items can be packed everywhere. They are not the problem. This branch of the literature, we are using the name by Codato and Fischetti, which appeared in 2006, but already the idea was somehow there in the work by Hooker a few years before. And so we get a stronger constraint, a combinatorial Benders cut constraint. Finding the minimal infeasible subset is NP-hard, is difficult, so one can use heuristic. We tried many ideas, but the basic one in which we remove small items one at a time and invoke white check as long as we remain infeasible, that is the idea that worked better in practice. So it's simple. You start from this set, you remove the small item one at a time, so white check, and you proceed until you get something infeasible. When you get something feasible, you stop, and then you found your smallest subset C. And this is a stronger constraint than the original one, but still not as strong as we would like. In fact, if you apply the decomposition with that constraint, you will see that Cplex, Gurobi, or anyway the solution solver will provide you solutions that are just slightly reshuffled. So you have some X variables at the next iteration after you add a constraint, you will get some slight variation of 1 unit on the left, 1 unit on the right. The good thing is that one can look for the interval of X coordinates, left.js, right.js, and build the interval of X coordinates for each item such that the cut will remain feasible. In practice, we can do it easily with an LP, with a linear program. We maximize the sum of the sides of these intervals. Here, we impose that, simply speaking, if an item J was overlapping with I in the previous solution, then it will still overlap. Then left is at the left of position P in the solution, and right is at the right of position P. And that's a linear program, so very easily. And once you solve it, you will obtain something which is stronger than the previous cut. We had one variable for each item. Now we have a set, an interval of variables for each item. And that produces less iterations in the decomposition scheme. So these are the two improvements that can be used. Let's see what we get in terms of a comparison with the literature. There were many works starting from Martello, Monaci, and Vigo 2003, and they used different time limits and different computers. Let's say we can think at a time limit of 20 minutes on a standard computer. And here you have many benchmark sets, and for each of them you have the size of the set, so how many instances in the set. You can see here the 10 classes have 500 instances. And here you can see the number of proven optimal solutions and in bold the best results. So you see that the composition is working very effectively, especially on the 10 classes. Still, we are not going into the details, but you could see that already in the 10 classes, there are instances with 20 items that cannot be solved to proven optimality. So there is still a gap between lower and upper bounds. So the strip packing problem is far from being solved. There is still more research to do. just the last detail on the problem, that is the time required to solve y check on the x-axis, and on the y-axis, the percentage of instances solved. So we said the problem is strongly NP-hard, so you can expect an asymptotic behavior. These are just the first 2 seconds. And with our ad hoc combinatorial branch and bound, we close very quickly feasible instances, 0.01 seconds or so, something like that. But we require more time to prove infeasibility. So that gave us the idea that more could be done for the solution of y-check. I'm skipping this one, and I'm going to the second application. The second application, we are using, again, our basic decomposition scheme, the one we used for the strip packing, but now we want to adapt it to the case of rotation. So each item can be rotated by 90 degrees. And that's a joint work with Maxence Delorme and Silvano Martello, appeared in 2017. So again, we use the same scheme as before, and we use a linear search between a lower and an upper bound on the strip 8. The first thing we need to do is take into consideration rotation. That is simply done in mathematical models for cutting and packing by doubling the number of items. We consider the original items from 1 to n, and then we create other n item copies. These item copies are obtained by rotating by 90 degrees the original item. So the width becomes the height, and the height becomes the width. So in practice, we have item j, which is the original item, and n plus j becomes the copy. And then the classical constraint is that either you choose the original item or you choose its copy. And that is true for each item j. And that allows to take a model that was working without rotation and use it to the case, adapt it to the case of rotation. Then, of course, much has to be done in case there are other techniques, not only the mathematical model is used. I'd like to discuss 2 improvements we made in this work, because again, I think they can be relevant for successive ideas or successive researches. The first one is the use of the arc flow formulations. So arc flow formulations are very old. They date back to the 60s or 70s, but they were taken to new life, let's say, by Valerio de Carvalho in 1999. The idea there is to represent items as arcs on a layered graph with a certain number of vertices. So let us suppose we have a strip whose width is W0 equal 10. So each vertex represents a partial bin filling, a partial width along the width of the strip. Let us consider this item with width 2 and height 7. We can pack it here, starting in the very left border of the strip, and we can represent it as an arc that goes from 0 to 2 and carry a height equal to 7. Or alternatively, we can rotate it and represent it as an arc that goes from 0 to 7 and carries a height equal to 2. We can, in fact, use this decomposition to model a feasible bar relaxation. So let us see how quickly. You suppose here you have, you want to check, you want to find this solution, and suppose the height is 8 here. So this item has height 7, and this item has height 2, 2, 2, and 2. You can represent this packing as a flow on a pseudo-polynomial model, on an arc flow model by de Carvalho. So you start from 0, which is this filling, and then you have some flow going out. You have a flow of value 7, which will go into 3, and then you have a 1 unit of loss space, which will go to 1, and then to 2, and to 3. You have 8 units of flow entering here, and then you have again 8 units leaving, 2, 2, 2, and 2 again. And these units will end up in the corresponding vertices. So what enters is equal to what leaves. I'm in depth with Maxence Delorme. Will in fact present more details on arc flow formulations for cutting and packing in the next talks, in the next talk. So we can solve the bar relaxation as an arc flow by imposing a flow conservation if you take any position P, you have that sum of what leaves minus what enters is equal to 0. With the exception of the origin, where you have H0 that is leaving, and the destination, when you have H0 that is entering. Then you have each item packed once, either in its original or copied variant, and then variables are integer. And that's the first improvement we discussed. The second is even simpler. We did nothing. Let's say it was ilog that worked for us, and they produce a very good solver for constraint programming. So instead of using a problem, yjp, where we had a binary variable for each item j in each position p, we use a new variable yj for each item j. So a smaller problem. Yj should be greater or equal than 0 and should respect the maximum height of the bin. And then we have this constraint, which is written in a constraint programming way. Among all the items that occupies column Q, then you consider all the intervals created by the items as the interval between yj, which is the height in which we pack the item, and yj plus hj, which is the height in which we finish the packing of the item. And these intervals should not overlap. And this problem can be implemented in 3 lines of code, and it works very effectively. There are still instances that the constraint programming cannot solve to proven optimality, but still it's very quick and effective. Let's see what we got in terms of solutions and comparison with the literature. We have the strip packing problem with rotation, the so-called stock cutting problem. Rectangle packing, in which we don't want to pack into the strip of minimum height, but into the square of minimum size. And pallet loading, in which we want to pack the maximum number of items having all the same size. And still there is larger literature. And you can see here our approach, again, 20 minutes on a standard computer. Maybe some of them were slower, so I apologize for that. But anyway, you can see here the number of proven optimal solutions in bold. And the new approach was always the best one, with the exception of pallet loading instances G, for which we had someone that was doing better. And it's difficult to solve these instances. I want to show you just 2 examples before we go to the last application. Here you can see an optimal solution for a pallet packing instance. That's very interesting because you can see even if you have 1 item, the rotation by 90 degrees make the problem very difficult. Like here you have a lot of non-guillotinable patterns. And in fact, sometimes the problem becomes not finding the good lower bound, but finding a heuristic solution, which is also optimal. And here you see another nice instance, the guard 21, which is a square packing instance. These are squares. You see them as rectangles because of the, I needed to fit into the slides, but in reality they are squares. And you see again, it's not easy to find such a packing in reality. So that is all also for the strip packing with rotation. So I'd like to mention the latest application we solved, which is a joint work with Jean-François Coté and Mohamed Awari, and it just appeared on InfoZone on Computing. And here we try to solve the bin packing, the 2-dimensional bin packing. And contrary to what's done in the literature, we do not use column generation or column generation-based heuristics, but we do the other way around. We start from the very basic textbook model for the 1-dimensional bin packing. Let's see it. We have a first variable, yi, that takes value 1 if bin I is used. Then a second binary variable, xij, that takes value 1 if item j is packed in bin I. We want to minimize the number of bins. We want each item to be assigned to a bin. And then constraint 19 here states that If we pack item j in bin I, then we have to consider its area, wj, hj, and the sum of the areas of all items packed into the bin should not exceed the area of the bin. So this is a relaxation of the original two-dimensional packing problem. We don't have overlapping anymore. If we consider just 19, we have just a redundant constraint. But it will be useful in the decomposition. The decomposition works because in 20, we have our Bender's cut or no good cut. Suppose we attended a solution in which a set S of items was assigned to a single bin. And suppose we proved that that was OPP infeasible, so two-dimensional infeasible, then we can remove this set for each item I, for each bin I in B, by saying simply that their sum, the sum of the variables associated to this set is at most the cardinality of S minus 1. And here I'm not going into the details, but you can expect that this can be lifted by combinatorial Benders cut, for example, or in many ways using the tricks from the literature. It is well known that the standard textbook model, you can call it Kantorovich or Martel and Toth, is weak for the one-dimensional bin packing. But in fact, here we are dealing with the two-dimensional bin packing. So this model is very quick in solving instances with 20, 40 items. So it's good enough for us. What we need to deal now is 20, these nasty constraints here. So again, I'd like to show you two improvements with respect to this basic decomposition. The first one is called meet in the middle patterns. And it's a joint work with Jean-François. And in fact, Jean-François will present it in a next talk during this conference, so I'm not spoiling it too much. But let's say out of the infinitely many solutions of a 2D packing problem, already in the 70s, they were restricting the space of solution, but taking only those that were bottom left aligned. Take the X variables, for example, the X coordinates. We want the packing to be left aligned. That reduces a lot symmetry. Now what we are doing is something different. We define a threshold cut value T, and if an item has its left border at the left of T, then we left align it. And if instead it has the left border at the right of T, then we right align it. And the reason by doing that is that there are three good reasons. The first reason is that we can compute the meet in the middle patterns with the same complexity required to find the normal patterns. It's the dynamic programming. In fact, the second good reason is that the size of the meet in the middle pattern is never higher than that of the normal patterns. You can see here, for a bin of size 30, the normal patterns are in a number 145 for the entire set of items. You can see here how the meet in the middle patterns change by changing the value of the threshold T. Here we are dividing more or less the bin into two, and we get to 125 patterns. We are reducing the number of variables in the bar relaxation. That's what we are doing. And in fact, with the same time complexity, we can also devise other pre-processing techniques, and we can reduce even further the number of patterns. So we have a smaller bar relaxation model. The other and very last improvement is instead focused on conservative scales. We are in the field of dual feasible function. I forgot to mention it here. So what is a conservative scale? It's a function that goes from 0, C, the interval 0, C, to again the interval 0, C, and in such a way that for any finite set S of integer, if this set had a sum that was below or at most equal to a certain capacity C, then also the modified item weights according to function F will be below this capacity C. So that was introduced by Johnson in 1973 with the term dual feasible functions. It was taken to new life by Fekete and Scheppers in 2001, and now it's served in a book by Claudio Alves, François Clotilde, Valerio Carvalho, and Ritz. And here you see an example. I cannot go into details, but suppose you are here, you have something, you are in the loss area. If you have something whose width is below 1/2 of the item of the bin width, then you suppose its width is 0. If it's in the middle, it remains in the middle. If it's above, you can raise it up to the entire bin width. In this way, you have modified the items in such a way that if a feasible packing existed for the original items, then it will also exist for the new items. The new items have new width, which are bar wj. And you can use a function to compute this bar wj and another function to compute the bar wh and obtain new cuts. And these new cuts are very important to raise the initial lower bound. The problem is that we have many functions to use. So how to devise good ones? Well, there are two ways. And again, that's the last technical slide of the talk. So I'm not going really into the details, but the first way is to devise a bilinear program. That's Caprara and Monaci 2009, in which we want to maximize the areas of the new items. And here, W bar j and H bar j are variables. And solving this bilinear program is difficult and it takes time. Here, what we use is a very effective and very quick heuristic by Belov, Kartak, Rowling, and Scheitauer, 2013, in which you first fix the height and compute by solving a simple LP the y bar variables. Then you fix the y bar variables and you compute the new age, the new height, and you continue like that. And if you're stuck, you use a conservative scale to start again. And this is very good and very, very effective. Let's see what we get, and then we will conclude the talk. We created two variants. The first one starts by executing the heuristic by Parreño, Alvarez Valdez, and Oliveira and Tamarit. And the second one simply takes in input the best known solution value. It's difficult to find a heuristic solution, so we took it from the literature. Here you can see the 500 instances from the 10 classes divided by items, from 20 items up to 100 items. Here you can see a lot of literature, again starting from 98 and ending up with our algorithm. And you can see here that the variant POUT with Parreño bound can solve 470 instances to prove an optimality. The variant with the best known solutions, which collect the best upper bound ever in the literature, can get up to 477 instances solved to prove an optimality. So it's a good improvement with respect to the literature. All instances with 20 items are solved, but they were solved already in 98. There are some instances with 40 items still unsolved. So even in this case, there is work to do to get better solutions. I'm skipping that one and I'm going to the concluding remarks. So cutting and packing problems are wide and interesting research areas. Many techniques have been developed for this area and then have been transposed into other areas. Think, for example, at column generation. The problems are very difficult and much has to be done both in terms of exact and heuristic methods. In the survey we published, which is the one on EJOR 2021, the concluding section contains a number of pointers with instances that are open problems. So a researcher interested in devising new exact method could just look at that section and see what remains to be solved. Alternatively, a number of variants arise every day from new decision problems, so there is plenty of room for future researches. Up to now, pseudo-polynomial models in mixed integer linear programming models have obtained better results than the disjunctive ones, or than pure constraint programs. But in fact, constraint programming appears to be a very promising future tool, even present tool, because we used it to solve the subproblem. But I believe there should be research done in this area in the next few years. That seems very promising. Personally, I'm now involved in two researches. One, together with colleagues from Karlsruhe, David Saya and Philip Fatt, we are doing a decomposition method for 2D strip packing problem that derives from a real application in the steel industry, in which they are building a stack, and so they have real data, and they have this conveyor coming, and we have the crane to pick up the items from the conveyor and put it into the stack, so we have precedences to be taken into account. And the other research I'm doing is together with Vinicius Lotti de Lima, Claudio Alves, François Clotiot, and José Manuel Valerio Carvalho, and we are surveying theoretical foundations and application of arc flow formulations. And we have a section devoted to cutting and packing. So thank you very much for your attention. Please let me know if you have any questions. I'll be glad to answer.
Thank you very much, Manuel. Thank you for a really very clear and informative talk. So we have, let's see if we have any questions. If it's, I was going to say, could you stop sharing your screen?
Yes.
So I can just see if anyone has put their hands up. What I can see is lots of people applauding.
Thank you. Now, how can I stopped sharing?
You have stopped sharing,
okay.
Yes.
Okay.
So do we have any questions from the audience? I'm hoping that I can spot the hands up versus the clapping. I've got a question in the chat. Jean-Francois, do you want to ask your question?
Yes, I can ask my question. Manuel, I was not aware of that second work that you presented. I was wondering if the linear relaxation of the bar relaxation is better in the second work than in the first work.
So you have a very similar relaxation, probably identical in practice, but you have less variables, so you are a little bit faster in getting it. And I don't know if there are counterexamples that can prove that one linear relaxation, the one with the basic model we used and the arc flow, is different, if these two relaxations are different or if they are the same. So I have no proof of equivalence and no counterexamples. But let's say they are similar. The arc flow uses a little bit less variables, so it's a bit quicker. That's the difference.
Thank you.
Okay. Any other questions? If people are struggling to put their hand up, Tony's found the hand up function. Tony, do you want to ask your question?
Okay, Tony.
I knew where it was, that function, by the way. No, the question is, could you explain in some general ways how you break the potential symmetry issues in the formulations? Is there any symmetry?
Yeah, there are a lot of symmetries in the last model, the one on the bin packing. So xij takes value 1 if we assign item j to bin I. We can build a solution in which item 1 is in bin 1 and item 2 is in bin 2. And if it's infeasible, the other way around, the other iteration, we could consider an alternative solution in which item 2, suppose they are identical, sorry, we have two items identical, in which item 2 is in bin 1 and item 1 is in bin 2. So that's a very known a problem of the Kantorovich model in bin packing. And we devised a number of symmetry breaking rules from the literature. I didn't discuss them in details, but let's say you can fix item 1 in bin 1, and you can fix item 2 either in bin 1 or in bin 2. And that's the first thing you do. Then you can do some more tricks, because when you prove that a subset of items cannot feasibly enter a bin, you don't have identical bins anymore, because item 1 will contain, bin 1 will contain item 1.
Yeah.
So the simple constraint that I showed in the slide in reality is not so simple in the implementation. But one has, thank you for the question, one has to deal with symmetries, otherwise the decomposition scheme will not work fine.
Okay, thank you. And thank you for the presentation, by the way.
Thank you.
It was really nice. Yeah.
Thank you. Okay, Jose.
Okay, thank you very much, Manuel. It was a big pleasure to hear your excellent talk. Congratulations. And my question is somehow related with the question that Tony has just put. It concerns symmetries, but more than that, it concerns the variant of the problem in which you assumedly have several copies of each item, because all the problems that you have tackled, they assume that items are all different, or if they are equal, we don't care. Then somehow they are assumed to be different. We don't take advantage of multiple copies of each item. And we also don't pay that price, of course. And my question is, how do you see the possibility of extending some of these formulations, or which formulation do you think is more keen on being extended for the case in which you have multiple copies of each item? Thank you.
So, thank you for the question, Jose. So indeed, it's very tricky to produce a no-good cut, a Bender feasibility cut for variables which are not binary. So if you have binary variables, you can take this variable and say, look, this can be 0 or 1. So their sum should be lower than or equal to a certain value. But if you have two variables that can take, suppose you get a solution in which the first variable has value 4 and the second variable has value 4, then you cannot simply say their sum should be lower than 8, because you are removing 3 and 5. So you are removing other subsets. So we used in the second work the trick by Francois van der Beek, in which you decompose in an integer variable using the power of 2. So a variable which can take value at most 8 is the sum of 4 variables. The first can take is multiplied by 1, the second by 2, the third by 4, and the fourth by 8. And it works somehow. But I believe there maybe something could be done with constraint programming. But I'm not an expert. I'm not an expert. But there it's where integer linear programming has some problems, some drawbacks. Thank you for the question.
Great. We've got a question in the chat from Mauro Russo. I saw you put your camera on. Would you like to ask your question?
Oh, sure. Thank you very much. I want to also congratulate to Manuel for the very good speech. I was just curious, maybe with previous question to Professor Oliveira, you answered to this. I was just curious to have seen some pictures with much more than 20 items pictured, because you said there are unsolved instances with up to 20 items.
So you can find the list of unsolved instances in our latest survey, but I think Jean-François Coté, who is here, published all our best solutions for the strip packing on the web. Maybe Jean-François can correct me if I'm wrong, because 7 years have passed since then. But I think we published the beam packing solutions. Did we, Jean-François? Please help me.
I have to check.
You have to check. Okay. But anyway, we have the solutions that were in output, in a LaTeX output, and you can see nice things by looking at the shapes and the patterns. And for the beam packing, all instances with 20 items are unsolved. Instances with 40 items are not. And there you can find many dense packings, like with 1 or 2 beams. So sometimes we have to pack 60 items in 2 beams, sometimes 40 items in a single beam. So the problem remains really the orthogonal packing problem, the very basic problem. It's the difficulty.
Okay, thank you.
I didn't publish them. I could.
We will. Thank you.
Okay. Any other questions? I just have one. It's great to hear you say there is still lots of work to still be done in two-dimensional rectangle packing. A sort of recent project I've been working on is the profit maximization problem with a single bin. And I think it's the first time I've worked on profit maximization rather than input minimization. So my question is, how would switching to a profit maximization problem, would the decomposition still work, or would that be a radical change?
Yes, it could work. Actually, what we did was to usually do a linear search between a lower and an upper bound, because we were lucky enough to have a small gap between lower and upper bounds. If we were not lucky enough, we asked Francisco Parreño to provide us with his code so we could reduce the gap between lower and upper bounds. And it could, the decomposition that we did could work with the maximization problem again with the search, but it depends on the quality of the bounds. So that has to be taken into account.
Great, thank you. Okay, are there any more questions? No? It's perfect timing. So in an effort to get some audience participation and interaction, if I could ask everyone to unmute their microphones, and then we can give our speaker a round of applause.
Thank you.
It still works. We can still give a round of applause as well as virtually, but physically. So thank you very much, Manuel, for being our opening keynote speaker. So we have a 15-minute break now. So we resume at 2:15 if you're in the UK, which I know is very few of us, 3:15 probably for the rest of you, and those elsewhere in the world, I'm sure you can work it out, it's in 15 minutes time. So see you back then. Bye-bye.